Hello everyone. In this lecture, I am going to explain about reduction of quadratic form to canonical form. So let's see the definition. Let x transpose Ax be a quadratic form in n variables. Then there exists a real non-singular linear transformation x equals to py, which transforms x transpose Ax to another quadratic form of type y transpose dy equals to lambda 1 y1 square plus lambda 2 y2 square plus and so on lambda n yn square. Then y transpose dy is called the canonical form of x transpose Ax. Here D is equals to diagonal matrix with the diagonal entries of lambda 1, lambda 2 and so on lambda n. Right? So here what is given? X transpose Ax. This is our quadratic form. Now we are finding canonical form of this quadratic form. So first, what is the definition canonical form? X transpose Ax be a quadratic form in n variables. Right? Now I am taking one non-singular linear transformation. What is the linear transformation? X equals to py. Right? So substitute this x equals to py in given quadratic form. Right? So that is also x equals to py means what we will get? X transpose Ax py whole transpose A into py. Right? So finally we will get y transpose p transpose ap of y. So here p transpose ap is also a symmetric matrix. So that means y transpose of p transpose ap of y is a quadratic form. If that quadratic form is sum of squares, then it is canonical form. And remember, in X transpose A is symmetric matrix, right? So if we substitute x equals to py, we will get another quadratic form. If that quadratic form is in the form sum of squares, then it is a canonical form, right? Let x transpose Ax be a quadratic form in n variables. Then there exists a real non-singular linear transformation x equals to py, which transforms x transpose Ax to another quadratic form of type y transpose dy is equals to lambda 1 y1 square plus lambda 2 y2 square plus and so on lambda n yn square. Then y transpose dy is called the canonical form of x transpose Ax. Now index of a real quadratic form. So index of a real quadratic form, the number of positive terms in canonical form or normal form of a quadratic form is known as the index, and it is denoted by small s. Right? So number of positive terms in canonical form of a given quadratic form. Signature of a quadratic form. So it is defined as the difference between the number of positive terms and the number of negative terms in its canonical form. So signature is defined as the difference between the number of positive terms and the number of negative terms in its canonical form. Now procedure to reduce quadratic form to canonical form by an orthogonal transformation, right? So x equals to py, that is the linear transformation, and p is non-singular. Suppose p is orthogonal matrix, then it is a orthogonal transformation. So x equals to py. If p is orthogonal matrix, then the transformation is orthogonal transformation. Now we see procedure. First, write the coefficient matrix associated with the given quadratic form. Second, find the eigenvalues of A, and third, write the canonical form using lambda 1 y1 square plus lambda 2 y2 square plus and so on lambda n yn square. And fourth one is form the matrix P containing the normalized eigenvectors of A as column vectors, then x equals to Py gives the required orthogonal transformation which reduces the quadratic form to canonical form, right? So by using canonical form, we can determine what type of quadratic, what type of given quadratics. So let's see one problem. Find the orthogonal transformation which transforms the quadratic form to canonical form. So this is our quadratic form. X1 square plus 3x2 square plus 3x3 square minus 2x2 x3, right? So the coefficient matrix A of the given quadratic form is A equal to, so coefficient of x1 square is 1, coefficient of x2 square is 3, coefficient of x3 square is 3. So already we know how to write the symmetric matrix corresponding to the given quadratic form. So A equals to 1 0 0 0 3 minus 1 0 minus 1 3. So now write characteristic equation, that is determinant of A minus lambda equals to 0. So that gives lambda cube minus 7 lambda square plus 14 lambda minus 8 equals to 0. By solving this polynomial equation, we will get roots. The roots are nothing but eigenvalues. Lambda equals to 1 comma 2 comma 4 and the eigenvectors. So we already know how to find eigenvectors. So when lambda 1 is equals to 1, so corresponding eigenvector is x1 equals to k times of 1 0 0 and lambda is equals to 2. So our eigenvector is k times of 0 1 1 and lambda 3 equals to 4. Eigenvector is k times of 0 1 minus 1. So for these vectors, we are calculating normalized eigenvectors. And here one important note, all eigenvalues are distinct. 1, 2 and 4, all are distinct. So corresponding eigenvectors are pairwise orthogonal. So if you take x1 and x2, they are pairwise orthogonal. Pairwise orthogonal means x1 transpose x2 equals to 0 or x2 transpose x1 equals to 0. So 1 into 0, 0, 0 into 1, 0, 0. And similarly, x2 and x3 are also pairwise orthogonal because the roots are distinct. If the roots are distinct, the corresponding eigenvectors are pairwise orthogonal. Now we normalize these eigenvectors. So the normalized vectors of the above eigenvectors x1 comma x2 comma x3 are, so E1 equals to x1 by norm x1, that is norm x1 value 1, E2 is equals to x2 by norm x2. So what is norm x2 value? Root 2, right? 0, 1 by root 2, 1 by root 2 and E3 is equals to x3 by norm x2, 0, 1 by root 2 minus 1 by root 2. So now write normalized model matrix. So this, take it as P cap. So P cap is equals to, so this vector you write it as first column, right? E1 write it as first column, E2 write it as second column, E3 write it as third column. And P inverse, just write P inverse. So P inverse is equals to 1 by root 2, root 2 0 0, 0 1 1, 0 1 minus 1. Clearly this P cap is orthogonal matrix. Pairwise orthogonal, right? The vectors are pairwise orthogonal and length of each vector is 1. So therefore P cap is orthogonal matrix. Furthermore, P inverse, P cap inverse, A into P cap is equals to D. Just to find out matrix multiplication, that give 1 0 0, 0 2 0, 0 0 4, right? Now consider the required non-singular linear transformation x equals to P cap of P cap y, that transforms the given quadratic form to canonical form. So I explained this thing in starting of this lecture. We know that the quadratic form is 2 equals to x transpose x, where x equals to p cap of y. So x equals to p cap y, I am substituting. So this is y transpose p cap whole transpose a into p cap of y. So clearly this is a, what about this? This is a quadratic form, right? And moreover, P inverse AP is equals to, by diagonalization, what is, sorry, P inverse AP? P inverse AP is equals to D. So how to write this? Y transpose dy we can write. So Y transpose dy, write this Y transpose dy. So therefore the canonical form is y1, y2, y3, and what is D? D equals to 1, 0, 0, right? This matrix is diagonal matrix, is formed by the diagonal matrix with the diagonal elements are nothing but eigenvalues 1, 0, 0, eigenvalues are 1, 2, 4. So y transpose dy, y1, y2, y3, 1, 0, 0, 0, 2, 0, 0, 0, 4, and y1, y2, y3. So simplifying this, y1 square plus 2y2 square plus 4y3 square. So this is our required canonical form. So what is the required orthogonal transformation? X equals to p cap of y, right? So we already know matrix p cap, and write y, y1, y2, y3, and what is x? X is x1, x2, x3, right? So this is our required orthogonal transformation. And what is rank? Rank is nothing but number of terms in canonical form. We have 3 terms in canonical form. So rank equals to 3. Index is number of positive terms. So all terms are positive. So index equals to 3. Signature is number of positive terms in canonical form minus number of negative terms in canonical form. So number of positive terms 3, no negative terms in canonical form. So signature is 3 minus 0 equals to